The Milky Way stretches across our night sky like a river of light, a band so familiar we rarely stop to think about what lies beyond it. But here's the unsettling truth. Defining where our galaxy actually ends is one of astronomy's most persistent challenges. The edge isn't a clean boundary like a coastline, it's a gradual fade into something far stranger and more complex than most people realize. Recent discoveries have revealed that what we thought was empty space beyond our galaxy is anything but. There are invisible halos of million-degree gas, ghostly streams of cannibalized galaxies, and a dark matter web extending nearly halfway to Andromeda. The Milky Way doesn't just stop, it bleeds into structures so vast they redefine what we mean by our galaxy. And the tools we're using to map these outer frontiers, from radio telescopes detecting neutral hydrogen to space observatories tracking individual star motions, are revealing a cosmos far more interconnected than we ever imagined. The stellar halo's ancient population. Beyond the Milky Way's bright spiral disk lies a structure that most people never see. The stellar halo, a nearly spherical cloud of ancient stars extending hundreds of thousands of light years in every direction. This isn't just empty space with a few scattered objects, it's a cosmic graveyard containing some of the oldest stars in existence. Metal-poor relics from when the universe was young and heavy elements were scarce. These stars don't participate in the orderly rotation of the galactic disk. Instead, they follow chaotic, highly elliptical orbits that take them on long journeys far above and below the plane, some travelling more than 150,000 light-years from the galactic centre before falling back inward. The first evidence for this halo emerged in the early 20th century, when Harlow Shapley studied globular clusters, dense spherical collections of hundreds of thousands of stars. He noticed these clusters formed a roughly spherical distribution around the Milky Way rather than concentrating in the disk. This was humanity's first hint that our galaxy had a three-dimensional structure far larger than the visible band of stars. Today we recognize the stellar halo as extending at least 300,000 light-years from the galactic center, possibly farther. Its stars are cosmic fossils preserving chemical signatures from the Milky Way's earliest epochs, when galaxies were smaller and metal production through stellar fusion had barely begun. What makes the stellar halo particularly fascinating is its origin story. Unlike the disk, which formed from collapsing gas clouds that settled into a rotating plane, the halo is largely built from galactic cannibalism. The Milky Way has spent billions of years capturing and shredding smaller galaxies, scattering their stars along elongated trajectories that now form the halo's spherical structure. Each merger added a new layer, like geological strata in rock. The Gaia spacecraft has revolutionized our understanding of this process by measuring the positions and velocities of millions of halo stars with unprecedented precision. By plotting their motions, astronomers have identified distinct groups of stars that once belonged to separate galaxies. One of the most significant discoveries is the Gaia Sausage-Enceladus merger, a massive collision that occurred approximately 10 billion years ago. A galaxy containing hundreds of billions of stars slammed into the young Milky Way, and the remnants of that ancient system now form a substantial portion of our inner halo. These stars can still be identified by their unique elongated orbits and extremely low metallicity. They contain only about 1/100th the heavy elements found in the Sunday. This chemical signature acts like a fingerprint, allowing astronomers to trace which stars were born in our galaxy versus which were immigrants from elsewhere. The stellar halo also contains spectacular stellar streams, long ribbons of stars torn from dwarf galaxies or globular clusters as they orbit through the Milky Way. The Sagittarius stream is among the most prominent, wrapping almost completely around our galaxy like a luminous scaffold. This stream comes from the Sagittarius dwarf elliptical galaxy, which is currently being ripped apart by our gravitational pull. As this smaller galaxy orbits, tidal forces stretch it into a long trail of stars extending across more than 1 million light-years. Observations of these streams allow astronomers to map the halo's shape and measure the gravitational pull of the Milky Way far beyond its visible edge. The density of stars in the halo decreases smoothly with distance, fading by orders of magnitude as you move outward. There's no hard boundary, just a gradual transition where the Milky Way's gravitational influence merges with that of neighbouring galaxies. In the outer halo, stars are separated by enormous distances, sometimes dozens of light-years apart. These regions are among the loneliest places in the galaxy. A star in the outer halo might have no neighbours visible to the naked eye, surrounded instead by the faint glow of distant galaxies. Chemical studies using spectroscopy have revealed that halo stars show a clear metallicity gradient. Stars closer to the galactic center tend to have slightly higher metallicity than those in the outer regions, suggesting the outer halo is composed primarily of debris from younger, chemically primitive galaxies captured early in the Milky Way's history. Some of these outer stars may have formed in galaxies that no longer exist, their parent systems completely dissolved into our halo over billions of years. The metallicity drops dramatically as you move from inner to outer halo, with some stars containing less than 1,000th the iron abundance of the Sunday. The stellar halo plays an essential role in determining the Milky Way's total mass. By observing the motions of globular clusters and distant halo stars, scientists can infer how much gravitational force the galaxy exerts at great distances. These observations consistently indicate that visible matter accounts for only a fraction of the mass required to explain the observed motions. The rest must come from dark matter, which dominates the halo's outer regions and extends far beyond the reach of any starlight. The stellar halo, therefore, serves as a visible tracer for an invisible structure, a lighthouse illuminating the edges of a much larger dark matter ocean. Globular clusters in the outer halo deserve special attention. Some orbit at staggering distances exceeding 150,000 light-years from the galactic center, marking the visible limit of the Milky Way's stellar domain. These clusters, containing some of the oldest stars in the universe, follow orbits so wide that they take billions of years to complete a single circuit. Palomar 4 and NGC 2419 are examples of these remote wanderers, barely bound to our galaxy, yet still gravitationally tied to it. Their motions help astronomers measure the total mass of the Milky Way, including its dark matter halo, by revealing how strong the gravitational pull is at these extreme distances. The hot gas corona, extending hundreds of thousands of light-years, surrounding the Milky Way's stellar components is something most people never imagine. A massive sphere of superheated gas called the galactic corona, extending potentially hundreds of thousands of light-years into space. This gas is so hot, temperatures reaching 1 to 3 million Kelvin, that it glows faintly in X-rays and ultraviolet light, invisible to human eyes but detectable by space-based observatories. The corona is extraordinarily diffuse, with densities of only a few particles per cubic centimetre, yet its total mass may rival or exceed all the stars in the Milky Way combined. This vast reservoir of ionized plasma represents one of the largest components of our galaxy, fundamentally changing how we define the Milky Way's true size. Hints of this hot halo first appeared in the 1960s when X-ray detectors aboard early space probes registered faint, diffuse radiation coming from all directions in the sky. Initially, astronomers thought these signals might originate from distant quasars or the cosmic microwave background, but further analysis revealed something closer to home. A significant portion of the soft X-ray emission originated from gas gravitationally bound to our own galaxy. Modern X-ray observatories like Chandra, XMM Newton, and Suzaku have mapped this corona in unprecedented detail, detecting emission from highly ionized elements such as oxygen-7, neon IX, and ions that have been stripped of most of their electrons. The corona extends at least 200,000 to 300,000 light-years from the galactic center, based on current observations, though some models suggest it stretches even farther, possibly approaching the halfway point between the Milky Way and Andromeda. If this is accurate, the coronas of our two galaxies may already be touching a quiet prelude to their eventual merger billions of years from now. The corona isn't uniform in structure. It appears denser and hotter near the galactic center, gradually thinning toward the outskirts. Embedded within it are cooler, denser clouds and filamentary structures, possibly remnants of small galaxies that were torn apart and mixed into the halo over cosmic time. The origin of this massive hot halo traces back to the Milky Way's formation through gravitational collapse and mergers. As the galaxy grew by accreting smaller systems, infalling gas was heated to extreme temperatures by gravitational compression and shock waves. Some of this gas cooled and condensed to form the stars and disk we see today, but a large fraction remained hot and diffuse, trapped in the galaxy's gravitational well. Over billions of years, energy injection from supernova explosions and stellar winds has continued to heat this halo, maintaining its high temperature despite some cooling through radiation. Observations of quasar light passing through the Milky Way's halo have provided crucial evidence for the corona's existence and structure. When light from a distant quasar travels through our galactic halo on its way to Earth, it passes through clouds of ionized gas that leave absorption lines in the quasar's spectrum. By studying these absorption features at different wavelengths, astronomers can identify which ions are present and determine the temperature and density of the gas. These studies have revealed a layered structure with hot inner gas surrounded by cooler, filamentary outer shells, confirming that the corona is not a simple spherical bubble, but a complex, multi-phase medium. The corona plays a critical role in the galactic ecosystem by acting as a reservoir for future star formation. Cooler gas clouds can condense out of the hot halo and rain down onto the galactic disk, replenishing the material needed to form new generations of stars. At the same time, energetic events such as supernova explosions and outflows from the central black hole push gas outward from the disk into the halo, enriching it with heavy elements forged in stellar cores. This creates a continuous cycle of inflow and outflow that links the disk to its vast surrounding halo in a delicate gravitational and thermodynamic balance. One of the most captivating features discovered within the corona is the pair of enormous Fermi bubble structures of high-energy radiation extending roughly 25,000 light-years above and below the galactic plane. Discovered by NASA's Fermi Gamma Ray Space Telescope, these bubbles are filled with hot plasma and energetic particles, likely ejected by the supermassive black hole Sagittarius A star during a period of intense activity millions of years ago. The bubbles demonstrate that the corona is not static but dynamic and turbulent, shaped by powerful events originating at the galactic center. Their sharp edges suggest they were created relatively recently in cosmic terms, perhaps within the last few million years. Estimating the total mass of the corona has proven challenging, but recent research combining X-ray observations with ultraviolet absorption measurements from the Hubble Space Telescope suggests it may contain up to half of the Milky Way's baryonic matter, the ordinary protons, neutrons that make up atoms. For decades, astronomers noted a discrepancy between the amount of ordinary matter predicted by cosmological models and the amount actually observed in galaxies. The discovery and characterization of the galactic corona has helped close this gap significantly. Much of the so-called missing baryonic matter has been found. It's simply too hot and diffuse to be detected easily by traditional observational methods. The corona's existence dramatically affects how we define the Milky Way's size. Traditionally, astronomers measured our galaxy's diameter using the distribution of stars or neutral hydrogen gas, marking the edge where densities dropped below detectable levels. But if the corona extends hundreds of thousands of light-years farther than the stellar disk, then the Milky Way's effective diameter approaches 1.5 to 2 million light-years when this extended hot halo is included. This makes our galaxy significantly larger than the simple disk-based measurements suggest, encompassing a volume comparable to the reach of its dark matter halo. Recent observations from the Erosta telescope have added another layer to our understanding by detecting even larger X-ray structures extending beyond the Fermi bubbles. These Erosta bubbles stretch nearly 45,000 light-years in each direction, forming a multi-layered system of galactic outflows. Together with the Fermi bubbles, they reveal that the Milky Way's central black hole has likely experienced multiple episodes of activity throughout its history, each one pumping energy and material into the surrounding corona and shaping its structure over millions of years. Dark matter's invisible architecture. The most massive component of the Milky Way is also the most mysterious. Dark matter, an invisible substance that makes up approximately 85% of the galaxy's total mass, yet has never been directly detected. This unseen material forms a vast halo, extending nearly 2 million light-years from the galactic center, roughly 10 times farther than the visible stellar disk. The dark matter halo is the Milky Way's true skeleton, the gravitational framework that holds everything together and determines the galaxy's ultimate size and shape. Without it, the visible galaxy would have flown apart billions of years ago, its stars scattered into intergalactic space by their own orbital velocities. Evidence for dark matter's existence emerged in the mid-20th century, when astronomers measured how fast stars orbit the galactic center. According to Newton's laws, objects farther from a gravitational center should orbit more slowly, just as outer planets in our solar system move slower than inner ones. But when scientists plotted the Milky Way's rotation curve, orbital velocity versus distance from the center, they found something unexpected. Beyond a certain radius, the rotation speed didn't decrease as predicted. Instead, it remained nearly constant even far beyond the visible edge of the galaxy. implying that substantial additional mass exists in regions where few stars are visible. This observation made no sense if only visible matter existed. The stars and gas we can observe simply don't provide enough gravitational pull to explain the high orbital speeds in the outer galaxy. The only explanation that fits the data is that the Milky Way must be surrounded by a massive halo of unseen matter, providing the extra gravitational force needed to keep those fast-moving stars bound to the galaxy. Early calculations suggested this dark halo might contain 10 times more mass than all visible stars combined, a staggering revelation that fundamentally changed our understanding of galactic structure. Estimating the shape and extent of the dark matter halo requires indirect methods since it cannot be observed directly through electromagnetic radiation. Astronomers study the orbits of globular clusters, satellite galaxies, and distant halo stars to measure the gravitational field at various distances from the galactic center. The faster these objects move, the more total mass must be present. Early models indicated that the Milky Way's dark matter halo extends at least 10 times farther than the visible disk, with recent measurements suggesting it reaches nearly 2 million light-years in diameter and contains between 1 and 2 trillion times the mass of our Sunday. Modern computer simulations have refined our picture of how dark matter halos form and evolve. In cosmological models like Illustris and Eagle, galaxies form when dark matter clumps together under gravity shortly after the Big Bang, creating gravitational wells that attract ordinary matter. That gas cools, condenses, and eventually forms stars and galactic disks. The visible galaxy is therefore just the central, luminous region of a much larger dark matter structure that extends far into intergalactic space. These simulations show that dark matter halos aren't perfectly spherical but slightly elongated, often resembling squashed spheres or triaxial ellipsoids rather than perfect balls. Interactions with nearby galaxies can further distort the halo's shape. The gravitational influence of Andromeda and the Magellanic Clouds stretches and tugs on the Milky Way's dark matter distribution over billions of years, creating asymmetries and substructures. Recent observations suggest our halo may be slightly flattened toward the galactic plane, and elongated in certain directions due to these external forces. The halo is not a static structure, but an evolving one, constantly responding to gravitational perturbations from its environment. The motion of stellar streams provides some of the best evidence for mapping the dark matter halo's properties. The Sagittarius stream, formed from a dwarf galaxy being torn apart by the Milky Way's gravity, traces a long, looping path around our galaxy. By modelling how this stream bends and twists under gravitational forces, scientists can map the underlying mass distribution, including the invisible dark matter. These analyses indicate that the halo extends far beyond the outermost visible stars, and that it may be slightly flattened rather than perfectly spherical, with its density decreasing smoothly with distance from the galactic center. Astronomers also use the escape velocity method to constrain the halo's total mass. This technique involves measuring how fast an object must travel to break free from the Milky Way's gravitational pull entirely. Recent data from the Gaia spacecraft tracking hypervelocity stars objects moving at extraordinary speeds through the galaxy show that even the fastest known stars remain gravitationally bound to the Milky Way. This observation implies an enormous gravitational reach, consistent with a dark matter halo mass of approximately 1.2 trillion solar masses, encompassing a region extending almost halfway to Andromeda. Although dark matter doesn't interact with light, it leaves indirect traces through gravitational lensing, the bending of light from distant galaxies as it passes through massive structures. Weak gravitational lensing surveys using instruments like the Hubble Space Telescope and facilities participating in the Dark Energy Survey have detected subtle distortions in the shapes of background galaxies caused by the Milky Way's dark matter halo. These measurements, though challenging to make, confirm that the halo extends far beyond the range of visible stars and contains the vast majority of our galaxy's mass. The galactic corona provides another independent line of evidence for dark matter. X-ray observations reveal that the Milky Way is surrounded by a sphere of hot ionized gas extending hundreds of thousands of light-years from the center. This gas should have escaped into intergalactic space long ago, unless something massive holds it in place. The amount of dark matter required to gravitationally bind this hot gas matches the estimates derived from rotation curves and satellite motions, strengthening the case for an extended, massive dark matter halo. One of the most intriguing aspects of the dark matter halo is its possible substructure. Cosmological simulations predict that dark matter halos should contain numerous smaller clumps or subhalos, invisible mini-structures orbiting within the main halo like planets around a star. Some of these subhalos may host small satellite galaxies like Draco or Fornax, while others might be entirely dark, containing no visible stars at all. Detecting these dark subhalos is extremely challenging, but astronomers are searching for them by looking for gravitational perturbations they might cause in stellar streams or through their subtle lensing effects on background light. Stellar streams tracing ancient mergers. Threading through the Milky Way's outer reaches are faint, ghostly ribbons of stars called stellar streams, the shredded remains of dwarf galaxies and globular clusters torn apart by our galaxy's relentless gravitational pull. These streams stretch across hundreds of thousands of light-years, invisible to the naked eye but revealed by modern surveys as elongated overdensities of stars moving in coordinated orbits. They represent some of the most dramatic evidence for galactic cannibalism, preserving a record of the Milky Way's violent past written in stars scattered along ancient orbital paths. Each stream tells the story of a smaller galaxy that ventured too close, was captured by our gravity, and slowly pulled apart over billions of years. The concept of stellar streams emerged in the late 20th century, when astronomers studying star distributions noticed thin trails that didn't belong to the galactic disk or known clusters. These weren't random alignments, their stars moved together as though they were once part of a single bound system. The Sagittarius stream remains the most spectacular example, formed from the Sagittarius dwarf elliptical galaxy currently undergoing tidal disruption as it orbits the Milky Way. This stream wraps around our entire galaxy in multiple loops, some portions lying above the galactic plane and others below, forming a stellar ribbon that encircles the Milky Way like a luminous thread wound around a sphere. When the Sagittarius dwarf first entered the Milky Way's gravitational field billions of years ago, tidal forces began pulling it apart. Each time the dwarf galaxy passed through the galactic disk or swung close to the center, more stars were stripped away and spread along its orbital path. Observations using data from the Sloan Digital Sky Survey and the Gaia spacecraft have mapped this stream in extraordinary detail, revealing multiple layers of stellar debris and even secondary loops, evidence that the disruption process has been ongoing for many billions of years. The stream contains stars of various ages and metallicities, providing clues about the formation history of the now doomed dwarf galaxy. The GD1 stream presents a different but equally fascinating case. This narrow trail consists of old stars that once belonged to a globular cluster. Unlike dwarf galaxies, globular clusters lack protective dark matter halos, making them more vulnerable to tidal disruption when they venture near the galactic center. GD1 stretches approximately 30,000 light-years across the sky as a thin line of stars, and careful observations have revealed gaps, small breaks in the otherwise continuous stream. These gaps may have been created by encounters with dark matter subhalos, invisible clumps that passed through the stream and gravitationally disturbed it, offering a rare indirect probe of dark matter's substructure. The Palomar 5 stream originates from a star cluster approximately 80,000 light-years from Earth, stretching across one-third of the sky in faint, thread-like arcs. Astronomers using data from Hubble and Gaia have confirmed that the cluster is slowly dissolving, its stars trickling away with each orbit through the Milky Way's gravitational field. The cluster's core is now so depleted that it may vanish completely within the next few 100 million years, leaving only the stream as evidence it ever existed. This gradual destruction illustrates how the Milky Way continuously grows by assimilating smaller systems, adding their stars to its extended halo. Stellar streams serve as sensitive probes of the Milky Way's gravitational potential. As a stream orbits through the galaxy, it traces the underlying distribution of mass, both visible and dark. Any distortion in the stream's shape or gaps in its structure can reveal where additional gravitational forces are acting. By studying the curvature, width, and velocity of streams, astronomers can map the galaxy's gravitational field with remarkable precision, revealing concentrations of dark matter and testing models of how mass is distributed throughout the halo. This technique has become one of the most powerful methods for studying dark matter on galactic scales. The patterns observed in stellar streams also allow scientists to detect dark matter subhalos predicted by cosmological simulations. If a dark matter clump passes near a stream, it creates a gravitational ripple that displaces stars, forming kinks or gaps in the stream's otherwise smooth distribution. By measuring these disruptions, Astronomers can infer the presence, mass, and even the abundance of dark matter structures too small and faint to be detected by any other means. This method, sometimes called galactic archaeology, turns the streams into fossil records that preserve information about both the Milky Way's assembly history and the nature of dark matter itself. Beyond serving as gravitational tracers, stellar streams provide time capsules from the early universe. Many stream stars are ancient, exceeding 10 billion years in age, and contain very low metallicity, far less than 1% of the Sun's heavy element abundance. These stars formed when the universe was young and supernova enrichment had barely begun, preserving chemical signatures from an era when galaxy formation was just getting underway. By analysing the compositions of stream stars through spectroscopy, scientists can reconstruct the environments in which their parent galaxies or clusters formed long before they were captured by the Milky Way. Some stellar streams intersect with the galactic disk, passing through regions of higher stellar density. When this happens, gravitational interactions can distort both the stream and the disk itself, creating oscillations or vertical waves that persist for millions of years. These interactions help explain subtle ripples recently observed in the Milky Way's outer disk using Gaia data signatures of ancient encounters between the disk and in falling satellite galaxies. The streams, therefore, don't just orbit passively through the halo, they actively shape the galaxy's structure through their gravitational influence. Recent surveys have dramatically increased the number of known stellar streams. Projects like the Dark Energy Survey, Pan-STARRS, and ongoing Gaia data releases have identified dozens of new streams, each representing a destroyed dwarf galaxy or disrupted cluster. Some are faint and narrow, barely visible above the background of halo stars, while others are broad and prominent, containing millions of stars spread across vast distances. Each new discovery refines our understanding of how the Milky Way grew through mergers and how common galactic cannibalism has been throughout its history. The halo, once thought to be a smooth distribution of old stars, is now recognized as a complex mosaic of debris from countless past encounters, the warped and flared galactic disk. For most of the 20th century, textbooks depicted the Milky Way as a neat, flat spiral, a perfect disk rotating around a bright central bulge. That simple picture has been shattered by modern observations, revealing that our galaxy's disk is neither flat nor symmetrical. Instead, it warps upward on one side and downward on the other, while simultaneously flaring outward at its edges like the brim of a hat. These distortions transform the Milky Way from an idealized geometric form into something far more dynamic and complex. A spinning structure constantly flexing and rippling under the gravitational influence of its neighbours and the uneven pull of its dark matter halo. The first hints that the Milky Way's disk was warped came from radio observations in the 1950s. When astronomers mapped neutral hydrogen gas across the galactic plane using the 2-1 centimeter emission line, they noticed that gas in the outer regions appeared displaced above and below the midplane. The pattern was consistent across multiple directions, suggesting a genuine physical warp rather than measurement error. At the time, it wasn't clear whether stars followed this same distortion or if the effect was limited to diffuse gas. But later infrared and optical studies confirmed that the stellar disk is also warped. Stars at the galaxy's outer rim beyond, about 40,000 light-years from the centre, rise thousands of light-years above the midplane on one side of the galaxy, and dip an equal distance below it on the other side. The total vertical displacement between the highest and lowest points can reach 10,000 light-years, creating a structure that resembles a vinyl record left in the sun too long, still spinning but with rippled edges. This warp starts to become noticeable around 12 kiloparsecs from the galactic centre and becomes more pronounced with increasing distance, affecting both the thin disk of young stars and the thicker disk of older stellar populations. The causes of this warping are complex and not yet fully understood, but gravitational interactions with nearby galaxies provide the most likely explanation. The large and small Magellanic clouds, orbiting roughly 200,000 light-years away, are massive enough to exert significant tidal forces on the Milky Way's outer regions. Computer simulations show that repeated encounters over billions of years could easily twist the disk into its current warped configuration. Additionally, the distribution of dark matter in the galaxy's halo may contribute. If the dark matter halo is not perfectly spherical but slightly elongated, its uneven gravitational pull would apply differential torque to the disk, bending it persistently into a warped shape. Beyond warping, the Milky Way's disk also exhibits flaring and thickening with distance from the galactic center. Near the core, the stellar disk is remarkably thin, only about 1,000 light-years thick, but at distances exceeding 60,000 light-years, that thickness increases to more than 3,000 light-years. This flaring occurs because the galaxy's gravitational pull weakens with distance from the center. In the inner regions, strong gravity confines stars and gas to a narrow plane, but in the outskirts, even small disturbances from passing dwarf galaxies, gas inflows, or motions within the dark matter halo can push material vertically out of alignment. Over billions of years, these vertical oscillations accumulate, creating the observed flare. Data from the Gaia spacecraft have revolutionized our understanding of these structural features. By tracking the three-dimensional positions and velocities of hundreds of millions of stars, Gaia has shown that both the warp and flare begin around 12 kiloparsecs from the center and intensify with distance. Beyond 40,000 light-years, the stellar layer can span several thousand light-years in height, and the warp's amplitude reaches its maximum. These measurements confirm that the Milky Way's outer disk is not a simple extension of its inner structure, but a distinct region shaped by different physical processes. Remarkably, the warp is not static, it precesses, rotating slowly around the galactic center like a wobbling plate. Gaia observations reveal that the entire warped pattern completes a full rotation roughly every 400 to 500 million years, driven by the combined gravitational influence of the central bar and the surrounding dark matter halo. This means the Milky Way's shape is continuously shifting, oscillating like a flag rippling in a breeze. From Earth's perspective, located about 26,000 light-years from the center and slightly above the midplane, this creates asymmetries in how we perceive the Milky Way's band. Across the night sky, the galactic plane appears to tilt upward near Sagittarius and downward near Cygnus, reflecting the disk's three-dimensional bend. The flare and warp aren't the only asymmetries. Radio surveys have revealed that the Milky Way's disk is also lopsided, with one half containing more gas and extending farther than the opposite side. This imbalance likely stems from past accretion of intergalactic material or gravitational disturbances created by orbiting companion galaxies. The side facing the Magellanic clouds appears particularly affected, suggesting their gravitational wake has created an asymmetric pull on our disk over billions of years. These features demonstrate that the Milky Way is far from equilibrium. It's a dynamically evolving system, still responding to past and ongoing interactions. Understanding the true shape of the Milky Way isn't merely an academic exercise, it's essential for reconstructing the galaxy's history. The warp and flare preserve information about gravitational forces acting over billions of years, each ripple and bend telling a story of interactions with smaller galaxies, infalling gas, and the dark matter halo's gravitational influence. By modelling these features, astronomers can infer how the Milky Way has interacted with its environment and even estimate the shape of the invisible dark matter halo that surrounds it, which remains one of the greatest unknowns in galactic astronomy. Recent data suggest the warp's motion could also affect star formation. As the outer disk bends, it compresses gas clouds unevenly, creating localized regions of higher density that can trigger bursts of new star formation along the warp's crests and troughs. The Milky Way, therefore, isn't just warped, it's alive with motion, renewal, and ongoing structural evolution. Far from being a static, unchanging backdrop, our galaxy is a dynamic entity shaped by billions of years of gravitational interactions, and its warped, flared disk stands as visible evidence of this tumultuous history. The galactic magnetic field's invisible currents. Threading through the Milky Way like invisible currents are vast magnetic fields that stretch across hundreds of thousands of light-years, influencing everything from the paths of cosmic rays to the birth of new stars. These fields are extraordinarily weak by terrestrial standards, averaging only a few microgauss, roughly 1/1,000,000th the strength of a typical refrigerator magnet. Yet their immense scale makes them powerful on galactic dimensions. Over distances of thousands of light-years, even such faint fields can channel the flow of ionized gas, shape the structure of the interstellar medium, and affect the overall dynamics of our galaxy in ways that remain incompletely understood. The first evidence for galactic magnetism emerged in the 1940s, when astronomers noticed that starlight passing through interstellar space was partially polarized, its light waves aligned along a preferred orientation. Polarization occurs when light scatters off dust grains that have been aligned by a magnetic field, revealing the field's direction. This simple observation demonstrated that the space between stars contains an ordered magnetic influence, rather than being magnetically chaotic. Later, radio astronomers detected synchrotron radiation radio waves emitted by electrons spiraling through magnetic fields at nearly the speed of light. These discoveries marked the birth of studies into galactic magnetism as a legitimate field of astrophysical research. The Milky Way's magnetic field runs roughly parallel to the galactic plane, following the spiral arms in large-scale loops and reversing direction several times between arms. This alignment suggests the field is tightly coupled to the galaxy's rotation and the flow of gas through its spiral structure. Scientists study the field using the Faraday rotation effect, in which the polarization angle of radio waves twists as they pass through magnetized plasma. By measuring how much rotation occurs across different regions of the sky, astronomers can infer both the strength and direction of the magnetic field along the line of sight. Data from surveys such as the Canadian Galactic Plane Survey and GALFAX reveal that the Milky Way's magnetic field follows a coherent spiral pattern with several reversals between spiral arms. These reversals are signatures of a large-scale dynamo mechanism, a process by which the motion of electrically conducting gas generates and sustains magnetic fields. Similar to how Earth's molten iron core produces our planet's magnetism, the galactic dynamo operates on enormous scales, driven by the differential rotation between the galaxy's inner and outer regions. As the inner disk rotates faster than the outer disk, it stretches and twists magnetic field lines, while turbulence in the ionized interstellar medium amplifies them, converting rotational kinetic energy into magnetic energy. This self-sustaining cycle has kept the galactic magnetic field alive for billions of years. Numerical simulations confirm that dynamos of this type can reproduce the field strengths and patterns observed in the Milky Way and similar spiral galaxies. Without the dynamo mechanism, galactic magnetic fields would have decayed long ago through resistive dissipation, yet observations show they remain strong and coherent, indicating that active amplification processes are continuously at work throughout the interstellar medium. Magnetic fields influence nearly every process in the interstellar medium, particularly star formation. When giant molecular clouds begin to collapse under their own gravity, magnetic pressure resists the inward pull, slowing the rate at which gas can condense into stars. Only when the magnetic field weakens locally or matter becomes sufficiently dense to overcome the magnetic support does gravitational collapse proceed, allowing new stars to ignite. In this way, magnetism acts as a regulator, preventing galaxies from converting all their gas into stars too quickly and extending the period over which star formation can occur. On larger scales, magnetic fields shape the filamentary structure of gas and dust visible in infrared observations. Data from the Planck Space Observatory show long strands of dust aligned with magnetic field lines, stretching across thousands of light-years and connecting regions of active star formation. These filaments trace the invisible currents threading through the galactic disk, guiding material into spiral arms and channeling gas flows that feed stellar nurseries. The magnetic field, therefore, doesn't just passively exist within the galaxy, it actively sculpts its structure and influences where and when new stars can form. The field also governs the behavior of cosmic rays, high-energy particles produced by supernova explosions and other violent events. Without magnetic fields, these particles would stream freely into intergalactic space, but instead they become trapped, spiraling along field lines and scattering through the galaxy for millions of years before finally escaping. This confinement creates a cosmic ray pressure that contributes to the dynamics of the interstellar medium and drives galactic winds slow outflows of material from the disk into the halo. These winds help regulate the galaxy's evolution by removing gas and metals from star-forming regions and distributing them throughout the halo. Beyond the galactic plane, magnetic fields extend vertically into the corona and potentially into intergalactic space. Observations of polarized radio emission reveal vertical magnetic structures rising tens of thousands of light-years above the disk, likely formed by outflows from supernova-driven winds or activity near the galactic center. These vertical filaments may channel hot gas and cosmic rays outward, linking the disk to the halo in a dynamic circuit that connects the Milky Way's different components. The magnetic field in this sense acts as a skeleton that binds the galaxy together across multiple scales. Recent studies have also explored how magnetic fields might interact with the Milky Way's central bar. As the bar rotates through the surrounding magnetized plasma, it can generate magnetic wakes and shock fronts that propagate through the disk, influencing gas flows and possibly triggering episodic bursts of star formation at the bar's ends. Understanding these interactions remains an active area of research, requiring detailed computer simulations and multi-wavelength observations to disentangle the complex interplay between gravity, rotation, and magnetism. The Fermi bubbles and galactic outflows. In 2010, astronomers analyzing data from NASA's Fermi Gamma Ray Space Telescope made a stunning discovery. Two enormous, symmetrical lobes of high-energy radiation extending roughly 25,000 light-years above and below the Milky Way's galactic plane. These structures, now known as the Fermi bubbles, are far larger than most features in the galaxy, dwarfing even the thickness of the visible disk. They glow faintly in gamma rays, X-rays, and microwaves, revealing that our galaxy's recent history included a violent energy release of staggering proportions, an event that reshaped the structure of the galactic halo and left behind these glowing monuments to past activity. For years before their discovery, astronomers had suspected unusual activity near the galactic center based on observations in radio and X-ray wavelengths that hinted at strange arcs and ridges of emission. But no one imagined structures on this scale until Fermi's detectors revealed them in their full extent. The symmetry was unmistakable. Two vast bubbles rising like plumes from the Milky Way's center, mirror images of each other, with sharply defined edges indicating that whatever created them acted both rapidly and powerfully. The energy required to form these structures is extraordinary, equivalent to roughly 100,000 supernova explosions combined, or about the total energy our Sun will emit over its entire 10 billion year lifetime. Each bubble contains tens of millions of solar masses worth of hot gas and relativistic particles moving at thousands of kilometers per second. The total energy stored in these structures is estimated at 10 to the 55th ergs, an almost incomprehensible amount that raises immediate questions about what could possibly generate such a phenomenon. Two major theories have emerged to explain the bubble's origin, both rooted in extreme activity near the galactic center. The first proposes that Sagittarius A star, the supermassive black hole at the Milky Way's heart, experienced a powerful accretion event in the relatively recent past. Normally, our central black hole feeds only sporadically on infalling gas, but like volcanoes, black holes can experience rare outbursts when sufficient material accumulates. During such a flare-up, gas spiraling inward would heat to millions of degrees and launch jets of plasma perpendicular to the galactic plane at nearly the speed of light. These jets would inflate the massive bubbles we observe today, carving cavities in the surrounding halo and accelerating particles to extremely high energies. This scenario is supported by observations of similar structures in other galaxies with active galactic nuclei, where powerful jets from central black holes create bubbles and lobes on even larger scales. The second hypothesis attributes the Fermi bubbles to an intense starburst event, a period of extraordinarily rapid star formation near the galactic center that triggered thousands of nearly simultaneous supernova explosions. The combined winds and shock waves from these explosions could have blasted hot gas into the halo with enough force to carve the twin lobes we see. Both explanations involve enormous power releases, and both fit the observational data reasonably well, making it difficult to definitively distinguish between them based solely on the bubble's current properties. The age of the Fermi bubbles remains uncertain, but most studies suggest they formed between 3 and 6 million years ago, a blink of an eye, in cosmic terms, but recent enough that they're still clearly visible today. This timing coincides intriguingly with evidence that Sagittarius A star was far more active in the recent past. Infrared observations show long, narrow filaments extending from the galactic center, possibly remnants of past jets or outflows. Even now, gas clouds near the core exhibit shock patterns consistent with recent violent activity from a powerful central source, supporting the black hole outburst scenario. The discovery took an even more dramatic turn in 2020, when NASA's Rosetta telescope detected even larger, fainter X-ray structures extending beyond the Fermi bubbles. These Rosetta bubbles stretch nearly 45,000 light-years in each direction, almost twice the size of the gamma-ray bubbles, forming a multi-layered system of nested outflows. Together, the Fermi and Rosetta bubbles reveal that our galaxy's central regions have likely experienced multiple episodes of energetic outbursts throughout recent history, each one pumping material and energy into the surrounding halo and leaving behind these expanding shells of hot plasma. The bubble's edges are surprisingly sharp, transitioning abruptly from high-energy emission to background levels over relatively short distances. This sharpness suggests the outflows that created them moved supersonically, driving shock fronts through the surrounding halo gas. As the expanding bubbles push outward, they compress and heat the material they encounter, creating the sharp boundaries observed today. The fact that these edges remain well-defined millions of years after formation indicates that the ambient halo gas is relatively low density, allowing the bubbles to expand freely without significant drag or disruption. Spectroscopic observations of gas within the bubbles reveal enrichment with heavy elements like iron and oxygen, suggesting the material was processed through stellar nucleosynthesis before being ejected. This finding supports both formation scenarios, whether the gas was heated by a black hole accretion disk or by supernova explosions. It would have been enriched with metals before being launched into the halo. The metallicity measurements provide valuable constraints on models of galactic outflows and help astronomers understand how energy and chemically enriched material are transported from the disk into the surrounding halo. The Fermi bubbles also demonstrate that galactic outflows aren't just theoretical constructs, but real observable phenomena shaping galaxy evolution. Similar bubbles and outflows have been detected in other galaxies, suggesting this is a common process in galactic evolution. These outflows help regulate star formation by removing gas from the disk, redistribute metals throughout the halo, and may even influence the galaxy's interaction with the surrounding intergalactic medium. Understanding the bubble's formation and evolution provides crucial insights into feedback processes that govern how galaxies grow and change over cosmic time. The Magellanic Stream and gas accretion, stretching across more than 200,000 light-years of space and wrapping halfway around the Milky Way, is one of the largest structures in our galactic neighborhood. The Magellanic Stream, an enormous arc of neutral hydrogen gas stripped from the large and small Magellanic Clouds as they orbit our galaxy. This vast filament contains roughly 500 million solar masses of gas, making it one of the most massive known examples of tidal stripping in the nearby universe. The stream represents active galactic cannibalism in progress, a vivid demonstration of how the Milky Way grows by capturing material from smaller galaxies that venture too close to its gravitational reach. The Magellanic Stream was discovered in the early 1970s through radio observations of neutral hydrogen at the 2.1 centimeter wavelength. Astronomers mapping the distribution of hydrogen around the Magellanic Clouds noticed faint emission extending far beyond the galaxies themselves, forming a long tail that wrapped around the southern celestial hemisphere. Subsequent observations revealed that this wasn't just gas escaping from the clouds, but a coherent stream following their orbital path, pulled out by the Milky Way's tidal forces as the dwarf galaxies travel through our halo. The stream originates primarily from the small Magellanic Cloud, which contains less mass than its larger companion, and is therefore more vulnerable to tidal disruption. As the clouds orbit the Milky Way, completing one revolution roughly every 1.5 billion years, differential gravitational forces stretch them along their orbital path. Gas on the side facing the Milky Way feels stronger gravitational pull than gas on the far side, creating a tidal stress that elongates the galaxies and pulls material away into space. Over hundreds of millions of years, this process has stripped enormous quantities of gas from the clouds, feeding the Magellanic Stream and leaving a trail that marks their passage through our halo. Recent observations have revealed additional complexity in the stream's structure. Beyond the main stream trailing behind the clouds, astronomers have detected a leading arm, a concentration of gas moving ahead of the Magellanic Clouds in their orbit. This leading arm contains gas moving toward the Milky Way's disk and will likely fall into our galaxy within the next few 100 million years, providing fresh fuel for future generations of star formation. The stream, therefore, represents not just material being stripped away but gas being actively transferred from one galaxy to another, a direct observation of how galaxies exchange matter throughout cosmic time. The Magellanic Stream also contains ionized gas in addition to neutral hydrogen. Observations using spectrographs aboard the Hubble Space Telescope and other facilities have detected highly ionized species like oxygen Z and carbon IV within the stream, indicating temperatures reaching hundreds of thousands of degrees. This hot gas likely results from the stream's interaction with the Milky Way's corona as the cool neutral hydrogen plows through the hot halo gas. Shock fronts form that heat and ionize the material. These interactions create a multi-phase medium within the stream, with cold neutral gas, warm ionized plasma, and hot shocked material, all coexisting in different regions. Chemically, the Magellanic Stream is relatively metal-poor compared to the Milky Way's interstellar medium, containing only about 1/10 the heavy element abundance found in our galaxy's gas. This low metallicity reflects the Magellanic Cloud's less evolved state. As smaller galaxies, they've experienced fewer generations of star formation and supernova enrichment than the Milky Way. When this metal-poor gas eventually falls onto our galactic disk, it will dilute the metallicity of local star-forming regions, potentially affecting the properties of stars that form from it in the distant future. The stream's trajectory can be traced using detailed radio maps that show its hydrogen distribution across the sky. From our perspective, it stretches in a great arc across the southern celestial hemisphere, beginning near the Magellanic Clouds and extending in the opposite direction from their current motion. Doppler measurements reveal that different portions of the stream move at different velocities, reflecting the complex gravitational interactions between the clouds, the stream material, and the Milky Way's dark matter halo. These velocity gradients allow astronomers to model the stream's three-dimensional structure and reconstruct its formation history. Computer simulations have successfully reproduced the Magellanic Stream's main features by modeling the orbital motion of the Magellanic Clouds through the Milky Way's halo over the past few billion years. These simulations show that the stream's current configuration is consistent with the clouds having made multiple passages through our halo, with each encounter stripping away more gas. The simulations also predict that the clouds will eventually merge with the Milky Way entirely, their stars and remaining gas being fully incorporated into our galaxy within the next few billion years, a process we can already see beginning through the ongoing formation of the Magellanic Stream. The stream provides a natural laboratory for studying gas accretion onto galaxies, a fundamental process in galaxy evolution. Galaxies don't form in isolation but grow continuously by accreting gas from their surroundings. The Magellanic Stream represents this process happening in real time in our own backyard, allowing astronomers to observe directly how gas flows from small galaxies onto larger ones, and how that gas is transformed as it falls through the halo toward the disk. Understanding these processes in detail helps refine our models of how all galaxies, including those in the distant universe, acquire the material they need for ongoing star formation. Recent observations have also detected stars within the Magellanic Stream, not just gas. These stars were likely stripped from the Magellanic Clouds along with the gas, and now follow similar orbits through the Milky Way's halo. Their presence demonstrates that tidal stripping can remove both gas and stars from satellite galaxies, contributing to the growth of the Milky Way's stellar halo in addition to replenishing its gas supply. The stream, therefore, represents a comprehensive example of galactic cannibalism affecting all components of the smaller galaxies involved. Globular clusters at the galaxy's edge. Orbiting in the outermost reaches of the Milky Way's halo are some of the most ancient objects in our galaxy. Globular clusters, dense spherical swarms containing hundreds of thousands to millions of stars packed into regions only dozens of light years across. These clusters are cosmic time capsules, preserving stars that formed more than 12 billion years ago when the universe was still in its infancy. What makes them particularly relevant to understanding the Milky Way's edge is that some orbit at staggering distances more than 300,000 light-years from the galactic center, marking the visible frontier of our galaxy's gravitational domain and providing crucial data for measuring its total mass. The Milky Way hosts approximately 150 to 200 known globular clusters, though more likely await discovery hidden behind dust lanes or obscured by crowded starfields. Unlike the loose open clusters found in the galactic disk, globular clusters are ancient and gravitationally bound so tightly that they've survived for most of cosmic history without dispersing. Their stars are predominantly old, metal-poor red giants and ancient white dwarfs, with ages comparable to the oldest stars in the universe. This makes globular clusters valuable probes of the early universe and the conditions that existed when the first generation of stars was forming. What's particularly striking about globular clusters is their distribution around the Milky Way. Rather than concentrating in the galactic disk like younger star clusters, globulars form a roughly spherical halo around the galaxy, with individual clusters following highly elliptical orbits that take them on long journeys far above and below the galactic plane. Some clusters, like 47 Tucanae and Omega Centauri, orbit relatively close to the galactic center, completing their orbits in a few hundred million years. Others, like NGC 2419 and Palomar 4, venture so far into the halo that their orbital periods exceed 1 billion years. NGC 2419 deserves special attention as one of the most distant globular clusters in the Milky Way's family, orbiting approximately 300,000 light-years from the galactic center. At this extreme distance, it's nearly halfway to the Andromeda galaxy, residing in the outermost frontier of our gravitational reach. The cluster moves through space so slowly that it takes roughly 3 billion years to complete a single orbit around the Milky Way. Its very existence at such a distance demonstrates that our galaxy's gravitational influence extends much farther than the visible stellar disk, providing important constraints on the total mass of the Milky Way, including its dark matter halo. Another remarkable outlier is Palomar 4, orbiting at roughly 360,000 light-years from the center, possibly the most distant known Milky Way globular cluster. These remote clusters are valuable precisely because their motions directly probe the galaxy's gravitational potential at extreme distances. By measuring their velocities and positions, astronomers can calculate how much total mass must exist within their orbits to keep them gravitationally bound. The results consistently indicate that dark matter dominates at these distances, with the dark matter halo extending well beyond the outermost clusters and possibly approaching the million light-year scale. Some globular clusters in the Milky Way may not be native to our galaxy at all, but were captured from smaller galaxies during ancient mergers. Omega Centauri, the most massive globular cluster in the Milky Way system, exhibits unusual properties that suggest it might be the stripped core of a dwarf galaxy that was consumed billions of years ago. Its stars show a range of ages and metallicities uncommon in typical globular clusters, which usually contain stars from a single formation event. This chemical complexity hints that Omega Centauri once belonged to a larger system that was torn apart by the Milky Way's gravity, leaving only this dense core behind. The chemical composition of globular cluster stars provides clues about the early universe's conditions. Most globular cluster stars contain less than 1% of the Sun's heavy element abundance, indicating they formed before significant supernova enrichment had occurred. By studying the detailed chemical fingerprints of these ancient stars through spectroscopy, astronomers can reconstruct the nucleosynthesis history of the early universe and understand which elements were produced in the first stellar generations. Some of the oldest globular clusters may contain stars from the second generation ever to form, born from gas enriched only by the first massive star's supernova explosions. Globular clusters also serve as testbeds for stellar evolution theory. Because all stars in a given cluster formed at roughly the same time from the same initial gas cloud, they provide natural laboratories for studying how stars of different masses evolve. By comparing observations of cluster stars with theoretical models, astronomers can refine their understanding of stellar life cycles, nuclear fusion rates, and the processes that govern how stars age. The most ancient globular clusters, with ages exceeding 12 billion years, help establish lower limits on the universe's age. It must be at least as old as its oldest stellar populations. The spatial distribution of globular clusters around the Milky Way reveals information about the galaxy's formation history. Clusters in the inner halo tend to be more metal-rich and may have formed during the galaxy's initial collapse, while outer halo clusters are more metal-poor and likely represent captured systems from mergers with smaller galaxies. This dichotomy supports hierarchical galaxy formation models in which large galaxies like the Milky Way assembled through the gradual accretion of smaller systems over billions of years. The globular cluster population, therefore, preserves a record of this assembly process written in the ages, orbits, and chemical compositions of its constituent stars. Recent discoveries have also identified stellar streams associated with disrupting globular clusters. Palomar 5, for example, is actively dissolving as tidal forces from the Milky Way's gravity pull it apart, creating long trails of stars stretching across the sky. These streams demonstrate that even ancient, tightly bound structures can be destroyed by persistent gravitational stress during close passages through the galactic disk or center. Over cosmic time, many globular clusters may have been completely dissolved, their stars now dispersed throughout the halo and indistinguishable from field stars. The clusters we observe today are survivor systems that happen to follow orbital paths, avoiding the most destructive tidal encounters. The Milky Way's motion through space. While we perceive the stars as fixed points on the celestial sphere, the truth is far more dynamic. The Milky Way itself is moving through space at extraordinary speeds, and Andromeda, participating in gravitational flows that span hundreds of millions of light-years, Our galaxy isn't stationary in an absolute sense, it's falling toward massive concentrations of matter, orbiting within larger structures, and being pulled by gravitational forces that extend across the observable universe. Understanding these motions provides crucial context for determining where the Milky Way truly ends and how it interacts with the cosmic environment beyond its visible boundaries. The most fundamental motion is the Milky Way's movement relative to the cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space. This radiation provides a natural reference frame for measuring absolute motion through the universe. Observations reveal that our galaxy moves at approximately 630 kilometers per second relative to the CMB, heading roughly toward the constellation Leo. This motion isn't random, it reflects the gravitational influence of massive structures in our cosmic neighborhood, pulling on the Milky Way and its nearby companions. Breaking down this motion reveals multiple components. First, the local group, the gravitational association containing the Milky Way, Andromeda, and about 60 smaller galaxies moves as a unit at roughly 630 kilometers per second toward a region of space in the direction of the constellation Centaurus. This bulk motion results from the gravitational attraction of the Virgo cluster, a massive concentration of over 1,300 galaxies located approximately 54 million light-years away. The Virgo cluster's enormous mass, exceeding 10,000 trillion suns, exerts a measurable gravitational pull on our local group, drawing us slowly toward it at a speed that won't result in merger for tens of billions of years, if ever, given the universe's accelerating expansion. But the Virgo cluster itself is moving, pulled by even larger structures. Beyond Virgo lies the Great Attractor, a gravitational anomaly located roughly 150 to 250 million light-years away in the zone of avoidance, the region of sky obscured by the Milky Way's thick disk. The Great Attractor appears to be a dense concentration of galaxies and dark matter, creating a gravitational basin toward which the Milky Way, Virgo, and thousands of other galaxies are falling. Measurements indicate our motion toward this region reaches several hundred kilometers per second when the Virgo cluster's influence is factored in. Even beyond the Great Attractor lies the Shapley supercluster, an enormous complex of galaxy clusters located approximately 650 million light-years away, containing more than 8,000 galaxies. Current evidence suggests that the Great Attractor is merely a foreground structure, and that the ultimate gravitational pull affecting our motion may originate from Shapley itself. This makes the Shapley supercluster potentially the deepest gravitational well, influencing the Milky Way's trajectory through space. Though at such vast distances, cosmic expansion driven by dark energy begins to dominate over gravitational attraction. These nested motions illustrate that the Milky Way exists within a hierarchical structure of gravitational flows. On the smallest scale, we orbit within the local group. On larger scales, the local group flows toward Virgo. Virgo in turn participates in larger scale motions toward the Great Attractor and Shapley. And all of these structures are embedded within the cosmic web, a vast network of galaxy filaments and voids spanning the entire observable universe. The Milky Way's location within a filament of this web determines its large-scale motion, with galaxies generally flowing along filaments toward dense nodes where galaxy clusters form. The discovery of Laniakea, a supercluster encompassing roughly 100,000 galaxies, including our own, refined our understanding of these motions. Laniakea, Hawaiian for immense heaven, represents the gravitational basin within which all galaxies share a common component of motion toward a central attractor region. The Milky Way sits near the outskirts of Laniakea, flowing along filaments toward its denser core. Mapping these velocity flows allows astronomers to define where one supercluster ends and another begins, revealing the large-scale structure that governs galactic motion across hundreds of millions of light-years. Within the local group, the Milky Way's most significant motion is toward the Andromeda galaxy. The two galaxies are approaching each other at approximately 110 kilometers per second, destined to collide in roughly 4 to 5 billion years. This motion reflects their mutual gravitational attraction, overcoming the general expansion of space at local scales. Unlike distant galaxies that recede from us due to cosmic expansion, Andromeda and other local group members are close enough that gravity binds them together, creating a future merger that will reshape both galaxies completely. Even the Milky Way's rotation constitutes a form of motion worth considering when defining its edge. The galaxy rotates differentially, meaning inner regions complete orbits faster than outer regions. Near the Sun's position, roughly 26,000 light-years from the center, the rotation speed is approximately 220 kilometers per second, giving our solar system an orbital period of about 230 million years. But in the outer halo and dark matter regions, rotation speeds remain surprisingly constant rather than declining as Newtonian physics would predict, providing key evidence for dark matter's existence and revealing that the galaxy's gravitational influence extends far beyond its visible components. Measuring these motions with precision requires sophisticated techniques. Astronomers use redshift measurements to determine how fast galaxies are moving away from or toward us, Doppler shifts in spectral lines to measure velocities, and proper motion studies tracking how objects change position on the sky over time. The Gaia spacecraft has been particularly valuable for measuring the Milky Way's internal motions, while large galaxy surveys provide the data needed to map flows across hundreds of millions of light-years, revealing the gravitational architecture that governs our galaxy's journey through space. The local group's gravitational boundaries. The Milky Way doesn't exist in isolation, but as part of a gravitationally bound family called the local group, a collection of more than 60 galaxies, spanning roughly 10 million light-years of space. Understanding this larger structure is essential for defining where the Milky Way's influence truly ends and where the gravitational domains of neighbouring galaxies begin. The local group represents the immediate cosmic neighbourhood, a region where mutual gravitational attraction has overcome the universe's expansion and bound these galaxies into an evolving system that will eventually merge into a single massive structure billions of years from now. The local group is dominated by two large spiral galaxies, the Milky Way and Andromeda, M31. Together, these two giants account for more than 95% of the local group's total mass. Andromeda is slightly more massive, containing approximately 1.5 trillion solar masses compared to the Milky Way's 1.3 trillion. Though both estimates carry significant uncertainties, primarily related to the extent of their dark matter halos. The third largest member is the Triangulum Galaxy, M33, a smaller spiral about half the Milky Way's size, orbiting in the space between the two giants, and likely gravitationally bound to Andromeda as a satellite. Surrounding these major galaxies is a swarm of dwarf companions, most orbiting the Milky Way or Andromeda. The Milky Way hosts at least 60 known satellite galaxies, though new ones continue to be discovered as surveys probe deeper into the halo. The large and small Magellanic clouds are the most prominent, easily visible from the southern hemisphere as glowing patches outside the Milky Way's disk. Others like Draco, Ursa Minor, Sculptor and Fornax are far fainter, containing only a few thousand to a few million stars each, and requiring sensitive instruments to detect. Some of these dwarfs are so dim they contain fewer stars than a single globular cluster, yet they count as galaxies because they're bound by their own dark matter halos rather than being tidally disrupted stellar streams. Andromeda possesses an even richer satellite system with more than 100 dwarf galaxies orbiting within its domain. Some, like M32 and M110, are visible in amateur telescopes as small elliptical companions. Others are being actively torn apart by Andromeda's tidal forces, forming streams of stars that wrap around its halo in patterns similar to those observed around the Milky Way. The distribution and properties of these satellite galaxies provide crucial information about the total masses and extents of their host galaxies' dark matter halos, helping astronomers map gravitational structures that remain invisible to direct observation. The local group's center of mass, called the barycenter, lies somewhere between the Milky Way and Andromeda, the gravitational midpoint where the pull of both galaxies balances. This point isn't fixed, but drifts slowly as the two galaxies approach each other on their collision course. Current estimates place it roughly 1.3 to 1.5 million light-years from our galaxy, though calculating its precise location requires accurate measurements of both galaxies' masses, which remain uncertain due to difficulties constraining their dark matter halos' extents. Beyond the immediate members orbiting the Milky Way or Andromeda, the local group extends to include smaller associations like the NGC 3109 subgroup and galaxies near the group's edges such as NGC 3109, Sextans A and Sextans B. These fringe members orbit near the zero-velocity surface, the boundary beyond which the universe's expansion overtakes the local group's gravitational pull. Inside this radius, currently estimated at roughly 5 million light-years from the local group's center, galaxies remain gravitationally bound, and will eventually be captured as the Milky Way and Andromeda merge. Beyond this boundary, galaxies recede faster than gravity can hold them, swept away by cosmic expansion into the larger universe. This zero-velocity surface represents a fundamental threshold defining the local group's extent. It's determined by balancing the gravitational attraction from the group's total mass against the Hubble expansion pulling space apart. As the Milky Way and Andromeda eventually merge over the next several billion years, their combined gravitational pull will strengthen, potentially expanding the zero-velocity surface and capturing additional galaxies that currently sit near the boundary. This growing sphere of influence illustrates how the local group evolves, not as a static collection but as a dynamic system, continuously exchanging matter and energy with its surroundings. The local group itself occupies a small region within the much larger Laniakea supercluster, positioned near the edge of a flattened structure called the local sheet, a planar arrangement of galaxy groups including the Maffei group, Sculptor group, and IC 342 group. These groups orbit within the larger gravitational flows toward the Virgo cluster and beyond toward the Great Attractor. The local group's position within this structure determines its motion through space and its eventual fate as cosmic expansion accelerates. One of the most intriguing aspects of the local group is its future evolution. Computer simulations clearly show that over the next 4 to 5 billion years, the Milky Way and Andromeda will collide and merge, forming a single giant elliptical galaxy sometimes called Milkomeda. This merger will fundamentally reshape both galaxies, destroying their spiral structures and mixing their stellar populations into a smooth, featureless elliptical. The Triangulum galaxy will likely be absorbed as well, either by Andromeda before the main merger or by the merged system afterward. Most of the smaller dwarf galaxies will either be consumed during the merger or remain as satellites orbiting the new combined galaxy. After the merger completes, the resulting Milkomeda system will gradually capture any remaining local group members through its enhanced gravitational pull. Over tens of billions of years, the entire local group will coalesce into a single massive structure, an island of light containing roughly 1 trillion stars. At the same time, cosmic expansion driven by dark energy will carry all other galaxies beyond the local group beyond our cosmic horizon, making them forever invisible and unreachable. The local group's boundaries, therefore, represent not just a present-day gravitational domain, but the ultimate limit of the observable universe for any future civilizations residing within the merged system. The Virgo supercluster's gravitational influence. Beyond the local group lies a much larger structure that profoundly influences the Milky Way's motion and evolution. The Virgo supercluster, an enormous complex of thousands of galaxies spread across roughly 110 million light-years. This vast gravitational district contains our local group, along with numerous other galaxy groups and clusters, all linked by the invisible threads of the cosmic web. The Virgo supercluster represents the broader cosmic neighborhood defining the Milky Way's place in the universe's large-scale structure and illustrating how gravitational attraction and cosmic expansion compete to shape the universe's ultimate architecture. The Virgo supercluster takes its name from its largest and most massive concentration, the Virgo cluster, located approximately 54 million light-years from Earth in the constellation Virgo. This cluster alone contains over 2,000 galaxies, bound together by an immense cloud of hot gas and dark matter with a combined mass exceeding 1 quadrillion solar masses. At its heart lie giant elliptical galaxies like M87, whose central black hole was famously imaged by the Event Horizon Telescope. These massive ellipticals formed through countless mergers over billions of years, growing to sizes far exceeding typical spiral galaxies like the Milky Way. Surrounding them are spirals, lenticular galaxies, and dwarf systems, all caught in a gravitational web constantly churning and evolving. The Milky Way sits far from this dense core, embedded in a quieter region near the supercluster's edge within a structure called the local sheet, a relatively flat arrangement of galaxy groups. This sheet includes the local group, the Maffei group, the Centaurus A group, and several others, all orbiting the Virgo cluster's massive gravitational center, much as moons orbit a planet, though on scales so large that their motions take billions of years to complete. The entire local group is falling toward Virgo at roughly 250 to 300 kilometers per second, though this motion is partially offset by flows toward even larger structures like the Great Attractor. For much of the 20th century, Astronomers considered the Virgo supercluster a distinct, isolated structure, an island of matter in an expanding universe. But modern observations reveal it's merely one region within an even larger entity, the Laniakea supercluster. Laniakea, meaning immense heaven, in Hawaiian, encompasses not only the Virgo supercluster but several adjacent clusters and filaments, stretching across 520 million light-years and containing roughly 100,000 galaxies. In this grander view, Virgo is just one dense knot in a cosmic web of vastly larger proportions, part of a hierarchical structure connecting our local universe across hundreds of millions of light-years. The discovery of Laniakea came through careful analysis of galaxy motions. Instead of moving randomly, galaxies follow streams converging toward gravitational centers where mass concentration is highest. By mapping these flow patterns using redshift surveys and peculiar velocity measurements, astronomers could identify where one supercluster ends and another begins. This analysis revealed that the Milky Way and its neighbors are being drawn toward a massive gravitational focal point deep within Laniakea, eventually traced to the region containing both Virgo and the more distant Great Attractor. Within the Virgo supercluster, gravity and cosmic expansion wage a delicate tug-of-war. On small scales within clusters and groups, gravity dominates, keeping galaxies bound together regardless of the universe's expansion. But on the largest scales approaching the supercluster's boundaries, Hubble expansion takes over, causing space itself to stretch and carry distant galaxies away faster than gravity can pull them back. The transition point lies around 100 million light-years, roughly the Virgo supercluster's traditional boundary. Inside this radius, galaxies generally move toward each other. Beyond it, cosmic expansion wins and galaxies recede into the larger universe. The filamentary structure of the Virgo supercluster reveals the cosmic web's architecture on intermediate scales. Galaxies aren't uniformly distributed, but form vast filaments and walls separated by immense cosmic voids, regions tens or hundreds of millions of light-years across containing very few galaxies. The Virgo filament connects our local group to the Virgo cluster through a chain of smaller groups including the Leo cluster and Coma Berenices cluster. These structures act like cosmic highways, channeling the flow of galaxies, gas, and dark matter along preferred directions where gravitational attraction is strongest. Studying the Virgo supercluster allows astronomers to understand how galaxy environment affects evolution. In the cluster's dense core, galaxies often lose their gas through ram pressure, stripping a process where motion through hot intracluster plasma pushes gas out of galaxies like wind stripping leaves from trees. This leaves them red, dead, and unable to form new stars, transforming spiral galaxies into passive ellipticals and lenticulars. In contrast, galaxies on the outskirts like the Milky Way remain gas-rich and actively forming stars. By comparing populations across different environments, scientists observe how surroundings determine galactic fate and evolution. The Virgo supercluster also provides crucial anchors for the cosmic distance scale, the ladder astronomers use to measure the universe's size and expansion rate. Variable stars, supernovae, and redshift measurements within Virgo have long been used to calibrate distances to more remote galaxies. These data underpin our understanding of cosmic expansion and help refine measurements of the Hubble constant, the rate at which the universe expands. Uncertainties in Virgo distances translate directly into uncertainties about the universe's age and ultimate fate. Despite its enormous size, the Virgo supercluster is not eternal. Over the next few billion years, cosmic expansion will continue pulling its outer regions apart while gravity concentrates material toward the densest clusters. Simulations suggest that in tens of billions of years, the entire supercluster might collapse into a single massive structure as the strongest gravitational concentrations merge, though cosmic expansion may prevent complete collapse. The ultimate fate depends on the balance between dark energy driving expansion and gravity pulling matter together, a cosmic competition whose outcome will determine the structure of the universe across deep time, the cosmic web's filamentary structure. When viewed from billions of light-years away, the universe reveals its secret architecture. Galaxies aren't scattered randomly through space, but form an intricate web spanning the entire observable cosmos. This cosmic web consists of filaments of dark matter, gas, and galaxies connecting to form a universal lattice, with enormous voids between them, vast regions so empty they contain almost nothing. The Milky Way, Andromeda, the Virgo supercluster, and even the Shapley concentration are merely tiny threads in this incomprehensibly large structure, part of a pattern that extends across 10 billion light-years and defines how matter is distributed throughout the universe. The concept of the cosmic web emerged during the 1980s when powerful computers first simulated how matter evolved after the Big Bang. Starting from tiny density fluctuations in the early universe minute, ripples visible in the cosmic microwave background, scientists watched gravity amplify these irregularities over billions of years. Denser regions attracted more material, while emptier regions became more vacant, creating the first stars, galaxies, and clusters. What emerged was astonishing. Rather than uniform distribution, the universe formed as a complex, interconnected network of filaments and nodes, with enormous bubble-like voids between them. The filaments of this web act as highways for matter, spanning hundreds of millions of light-years and channeling gas, galaxies, and dark matter into dense nodes where galaxy clusters form. Between these filaments lie cosmic voids, vast, bubble-like expanses, sometimes exceeding 300 million light-years across, containing just a handful of galaxies or none at all. These voids are the emptiest regions known in the universe, some with densities less than 1% of the cosmic average. The universe's large-scale structure, therefore, resembles Swiss cheese or foam, with matter concentrated along intersecting walls and filaments surrounding empty bubbles. Observational confirmation of this predicted structure came from large galaxy surveys beginning in the 1980s. The CFA Redshift survey mapped thousands of galaxy positions in 3 dimensions, revealing long filaments connecting dense clusters with enormous voids between them. Later projects like the Sloan Digital Sky Survey and 2DF Galaxy Redshift Survey mapped millions of galaxies, and when plotted in 3 dimensions, the distribution matched simulations perfectly. Long filaments of galaxies connecting clusters, surrounding enormous, nearly spherical voids. The largest known structure, the Hercules Corona Borealis Great Wall, stretches more than 10 billion light-years, so enormous it spans nearly 1/10 of the observable universe. Dark matter forms the foundation of this structure. Comprising roughly 85% of all matter in the universe, dark matter is invisible to electromagnetic radiation, but provides the gravitational scaffolding along which normal matter flows. After the Big Bang, dark matter clumped first, forming filaments and halos under gravity's pull. Normal matter, hydrogen and helium gas, followed these dark matter streams, cooling and collapsing where density peaked to form the first stars and galaxies. Without dark matter's gravitational framework, galaxies couldn't have formed at all. The universe would be a nearly uniform fog of gas with no structure whatsoever. Each filament contains a mixture of galaxies, hot plasma, and dark matter bound together across unimaginable distances. Observations from X-ray telescopes and ultraviolet spectrographs have revealed the warm-hot intergalactic medium, tenuous gas-filling spaces, between galaxies, heated to millions of degrees as it falls into filaments along gravitational potential gradients. This WIM may contain the universe's so-called missing baryons, ordinary matter unaccounted for in earlier surveys. The cosmic web, therefore, isn't just a structure of galaxies, but the reservoir of all matter, visible and invisible, distributed across the universe according to gravity's ancient blueprint. Filament intersections form nodes where multiple matter streams converge, giving birth to massive galaxy clusters like Virgo, Coma, and Shapley. Each cluster sits at a junction where gravity has gathered tremendous amounts of material over billions of years. The Milky Way resides within one such filament as part of the Laniakea supercluster, which flows toward the gravitational basin centered near the Great Attractor and Shapley regions. Our position within this structure determines our motion through space and our gravitational connections to surrounding galaxy groups and clusters. The cosmic voids, though seemingly empty, play equally important roles. They expand faster than the universe's average rate, pushing matter outward toward filaments and helping shape the web's overall pattern. Galaxies near void edges experience a kind of gravitational push away from the void's center, influencing their velocities and potentially affecting large-scale cosmic flows. Astronomers study these motions to understand the balance between gravity and dark energy, the mysterious force driving the universe's accelerated expansion, and determining its ultimate fate. What makes the cosmic web remarkable isn't just its size, but its self-similarity across scales. From distributions of galaxies to clustering of dark matter, the same filamentary patterns repeat themselves like cosmic fractals. Even on the Milky Way's scale, local filaments of gas and dark matter reflect patterns found in the universe at large. The web's structure appears roughly the same whether viewed from distances of millions or billions of light years, suggesting that the same fundamental physical laws govern structure formation across all cosmic scales, from individual galaxies to the universe itself. Computer simulations like Illustris and Eagle have reproduced the cosmic web structure with remarkable fidelity by modelling how dark matter and ordinary matter interact under gravity, from the Big Bang to the present. These simulations show filaments forming early in cosmic history, then growing and evolving as matter continues flowing along them. Galaxies form where filaments intersect, fed by continuous streams of gas that replenish their star-forming reservoirs. The simulations predict that this pattern will persist into the future, though cosmic expansion driven by dark energy will eventually freeze growth, stretching filaments until they break and isolating galaxy clusters from each other in an ever-expanding universe. Mapping the cosmic web continues as one of astronomy's grand challenges. Projects like the Dark Energy Spectroscopic Instrument and the upcoming Vera Rubin Observatory will map billions of galaxies across cosmic time, revealing how the web evolved and how dark energy affects its growth. Understanding this structure helps answer fundamental questions about the universe's composition, its history, and its ultimate fate, whether it will expand forever, recollapse, or reach some stable configuration depends on the interplay between matter's gravity and dark energy's repulsive pressure, forces that have shaped the cosmic web since the beginning of time. Intergalactic medium and missing baryons. Between the galaxies lies not empty space but a vast ocean of extremely diffuse gas called the intergalactic medium, a tenuous plasma extending throughout the cosmic web and filling the voids between galactic clusters and filaments. For decades, astronomers noticed a puzzling discrepancy. Observations of galaxies and galaxy clusters accounted for only about half the ordinary matter predicted by cosmological models based on the Big Bang and observations of the cosmic microwave background. The rest, called the missing baryonic matter problem, remained undetected despite extensive searches. The solution turned out to be hiding in plain sight within this intergalactic medium, spread so thinly and heated to such extreme temperatures that it evaded detection by traditional observational methods. The intergalactic medium exists in multiple phases, with vastly different temperatures and densities. The coolest phase consists of neutral hydrogen clouds at temperatures around 10,000 degrees Kelvin, detectable through absorption lines they create in the spectra of distant quasars. When light from a quasar travels through these hydrogen clouds on its way to Earth, atoms absorb specific wavelengths, creating a pattern of lines called the Lyman alpha forest. By studying these absorption features, astronomers can map the distribution of cool gas throughout the universe and trace how it has evolved over cosmic history. But the coolest phase represents only a small fraction of the intergalactic medium's total mass. The bulk resides in a much hotter phase called the warm-hot intergalactic medium WIM, heated to temperatures between 100,000 and 10 million degrees Kelvin. This gas is so hot it's fully ionized. Electrons have been stripped from their atoms, making it invisible to most observational techniques. It doesn't absorb optical light significantly, doesn't emit strongly in radio wavelengths, and only reveals itself through subtle absorption or emission features in ultraviolet and X-ray wavelengths that require space-based observatories to detect. The WIM pervades the cosmic web's filaments, tracing the same large-scale structure as galaxies but extending far beyond visible galactic distributions. As matter falls into gravitational potential wells along cosmic filaments, it accelerates and heats through shock waves and gravitational compression, reaching temperatures of millions of degrees. This process converts the kinetic energy of infalling material into thermal energy, creating a hot diffuse plasma that fills the space between galaxies. The WIM contains roughly 40 to 50% of all baryonic matter in the present-day universe, more than all the stars in all the galaxies combined. Detecting the WIM requires sophisticated observational techniques. Ultraviolet spectrographs aboard satellites like the Far Ultraviolet Spectroscopic Explorer and instruments on the Hubble Space Telescope have detected absorption lines from highly ionized species like oxygen-5 and nitrogen-5 in the spectra of distant quasars and active galactic nuclei. These absorption features indicate the presence of hot gas along the line of sight, allowing astronomers to map the WIM's distribution. Similarly, X-ray observatories like XMM Newton and Chandra have detected emission lines from oxygen 7 and 8 in the spectra of galaxy clusters and filaments, revealing hot gas glowing faintly in X-rays. The challenge in detecting the WIM lies in its extremely low density. Even in regions where it's relatively concentrated, densities reach only a few particles per cubic meter, far more tenuous than the best laboratory vacuum achievable on Earth. At such low densities, the gas emits very faint radiation, requiring long observation times and sensitive instruments to detect. Furthermore, foreground emission from our own galaxy's hot halo can contaminate measurements, making it difficult to distinguish intergalactic signals from local sources. Despite these challenges, systematic surveys have gradually built up a statistical picture of the WIM's properties and distribution. Recent observations using the technique of stacking, combining signals from many lines of sight to increase sensitivity, have confirmed the WIM's existence and abundance. By analyzing absorption features in hundreds or thousands of quasar spectra simultaneously, astronomers achieve sufficient signal-to-noise to detect the faint signatures of hot intergalactic gas. These studies show that the WIM is concentrated along cosmic filaments connecting galaxy clusters, exactly as simulations predict, confirming that it represents the long-sought missing baryonic matter. The WIM plays a crucial role in galaxy evolution by serving as a reservoir from which galaxies can draw fresh gas for star formation. Cooler streams of gas can condense out of the hot medium and flow along filaments toward galaxies, replenishing gas consumed by star formation or expelled by supernova-driven winds. This process, called cold mode accretion, allows galaxies to sustain star formation over billions of years despite continuously converting gas into stars. Without the WIM serving as a reservoir, galaxies would have exhausted their gas supplies long ago and ceased forming new stars. The WIM also carries the chemical history of galactic evolution. Supernovae and stellar winds from galaxies eject metal-enriched gas into their surroundings, where it mixes with the intergalactic medium. Over cosmic time, this process has gradually enriched the WIM with heavy elements, raising its metallicity from essentially zero shortly after the Big Bang to roughly 1/10 the Sun's metallicity in the present epoch. By measuring metallicities in the WIM at different cosmic distances, astronomers trace how galactic feedback has processed and redistributed matter throughout the universe's history. Future observations will continue refining our understanding of the intergalactic medium. Next-generation X-ray telescopes like XRISM and the proposed Athena mission will provide improved sensitivity and spectral resolution for detecting WIM emission and absorption features. These observations will map the WIM's distribution in unprecedented detail, revealing how gas flows through the cosmic web and how galaxies interact with their surrounding environment across cosmic time. Dark energy's role in defining boundaries. While gravity pulls galaxies together and dark matter provides the invisible scaffolding for cosmic structure, another force works in opposition, stretching space itself and ultimately determining where the Milky Way's gravitational influence truly ends. Dark energy, the mysterious force driving the universe's accelerated expansion. This invisible pressure dominates the cosmos, comprising roughly 68% of the universe's total energy density and growing stronger relative to matter as the universe expands. Dark energy doesn't tear galaxies or atoms apart directly. Its effects are immeasurably small on local scales, but across hundreds of millions of light years, its influence becomes overwhelming, ultimately defeating gravity and determining the boundaries of all gravitational structures, including the Milky Way. Astronomers discovered dark energy accidentally in the late 1990s through studies of distant Type-Ia supernovae stellar explosions that serve as standard candles for measuring cosmic distances. Two independent teams found that distant galaxies were farther away than expected if the universe's expansion was slowing under gravity's pull. The only explanation was that expansion itself was accelerating, driven by some unknown repulsive force acting throughout space. This discovery revolutionized cosmology and earned its discoverers the 2011 Nobel Prize in Physics. But it also introduced one of science's deepest mysteries, the nature of the force causing this acceleration. The leading theoretical explanation invokes Einstein's cosmological constant, denoted by the Greek letter lambda, which represents energy inherent to space itself. According to quantum field theory, even empty space contains energy from virtual particles constantly appearing and disappearing. This vacuum energy exerts negative pressure, effectively a repulsive gravitational effect that pushes space apart. As the universe expands and more space appears, more vacuum energy is created, driving ever faster expansion in a runaway feedback loop. The cosmological constant predicts that this acceleration will continue indefinitely, eventually dominating all other forces. Alternative theories propose that dark energy might not be constant, but could vary over time through a hypothetical scalar field called quintessence. Unlike the cosmological constant, quintessence's energy density could change as the universe evolves, potentially growing stronger or weaker over cosmic time. Some models even suggest modifications to general relativity itself might be needed on cosmological scales, with gravity behaving differently than Einstein predicted across billions of light years. Despite extensive theoretical work, dark energy's true nature remains one of physics' greatest unsolved problems. For structures like the Milky Way, dark energy's effects define ultimate boundaries in a fundamental way. Currently, our galaxy remains gravitationally bound to its local group companions because their mutual gravitational attraction overcomes cosmic expansion at these small scales. The Milky Way and Andromeda are close enough separated by about 2.5 million light-years that their gravity pulls them together despite the universe's expansion, explaining their eventual collision in roughly 4 billion years. But beyond the local group's zero-velocity surface at approximately 5 million light-years, expansion dominates and galaxies recede faster than gravity can pull them back. This zero-velocity surface represents the ultimate boundary of the Milky Way's future gravitational domain. Galaxies beyond this radius are being carried away by expanding space and will never be captured no matter how long we wait. Over the next 100 billion years, dark energy will expand the universe so much that all galaxies beyond our local group will disappear beyond the cosmic horizon, the distance from which light can ever reach us, given the finite age and expansion of the universe. To any observers within the merged Milky galaxy billions of years hence, it will appear that their system is alone in an otherwise empty universe, with all evidence of other galaxies stretched beyond detectability. The current expansion rate, called the Hubble constant, is approximately 70 kilometers per second per megaparsec, meaning that for every 3.26 million light-years of distance, a galaxy's recession velocity increases by another 70 kilometers per second. At distances exceeding about 4.5 billion light-years, galaxies recede faster than light speed, not because they're moving through space that quickly, but because the space between us and them is expanding. This doesn't violate relativity because nothing is actually moving faster than light through space. Rather, space itself is stretching, carrying distant galaxies beyond our reach. The future depends critically on how dark energy evolves. If it remains constant as the cosmological constant predicts, the universe will expand exponentially forever, with the distance between unbound structures growing without limit. Galaxies beyond gravitationally bound groups will drift away into isolation, eventually becoming invisible as their light is redshifted beyond detectability. This scenario leads to what cosmologists call the Big Chill or heat death, a universe that becomes increasingly cold, dark, and empty as expansion continues indefinitely. However, if dark energy strengthens over time, a more catastrophic fate called the Big Rip could occur. In this scenario, acceleration becomes so extreme that it eventually overcomes all forces, even gravity on galactic and atomic scales. First, galaxy clusters would separate. Then individual galaxies would be torn apart. Eventually, stars, planets, and even molecules could be shredded as space expands faster than light can travel between their constituent particles. Current observations suggest the Big Rip, if it occurs at all, lies at least 20 billion years in the future, but its possibility illustrates how dark energy ultimately determines not just where galaxies end, but whether they can continue existing at all. Measurements of dark energy's properties continue through large surveys, mapping the distribution and recession velocities of millions of galaxies across cosmic time. Projects like the Dark Energy Survey, Baryon Oscillation Spectroscopic Survey, and upcoming missions like Euclid and the Nancy Grace Roman Space Telescope will constrain how dark energy has evolved over billions of years, testing whether it's truly constant or changing. These observations will determine whether the cosmological constant provides the correct description or whether new physics is needed to explain cosmic acceleration. The Milky Way's ultimate future. The Milky Way appears permanent from our brief human perspective, its spiral arms seemingly eternal features of the night sky. But on cosmic timescales, our galaxy is merely a temporary configuration of matter destined for dramatic transformation. The forces already at work, gravitational attraction, galactic mergers, star formation depletion, and cosmic expansion have written a detailed script for the Milky Way's future, extending billions of years ahead. Understanding this fate requires examining how our galaxy will evolve through collision with Andromeda, the gradual exhaustion of its gas supplies, and ultimately its isolation in an ever-expanding universe driven by dark energy. The most significant chapter begins in approximately 4 billion years, when the Andromeda galaxy, currently approaching at 110 kilometers per second, finally collides with the Milky Way. Despite the word collision, the encounter won't be immediately destructive. The space between stars is so vast that stellar collisions will be extraordinarily rare. Most stars will pass harmlessly between each other. The true collision occurs between gravitational fields, gas clouds, and dark matter halos. As Andromeda approaches, its gravity will distort the Milky Way's spiral structure, pulling long tidal tails of stars and gas into intergalactic space like streamers trailing behind the galaxies. When the galactic disks finally interpenetrate, gravitational interactions will compress clouds of hydrogen throughout both galaxies, triggering spectacular bursts of star formation. New clusters of brilliant blue stars will ignite across tidal bridges connecting the two systems, briefly increasing their combined luminosity. From Earth, if it still exists, the night sky will transform beyond recognition as Andromeda swells from a faint smudge into a vast spiral dominating the entire sky. Over several 100 million years, the two galaxies will begin to merge, their spiral arms unwinding and their distinct identities dissolving. After the initial close pass, gravity will pull the galaxies back together for additional encounters. Computer simulations show they'll swing past each other several times over roughly 1 billion years, each passage stripping away more angular momentum and pulling the systems closer together. Eventually, they'll merge completely into a single enormous elliptical galaxy containing nearly 1 trillion stars. This new galaxy, nicknamed Milkomeda, will bear little resemblance to either parent. It's smooth. The featureless structure will show no trace of the beautiful spiral arms that characterize both the Milky Way and Andromeda. At Milkomeda's center, the supermassive black holes from both galaxies Sagittarius A star and Andromeda's central black hole will spiral toward each other, their orbital dance releasing tremendous amounts of energy in gravitational waves. These ripples in space-time will propagate outward at light speed, detectable by any sufficiently advanced civilizations within hundreds of millions of light years. When the black holes finally merge after billions of years, they'll form a single supermassive black hole containing roughly 100 million solar masses, reigning at the merged galaxy's heart. The merger will redistribute our solar system's position within the new galaxy. Depending on the precise geometry of the collision, the Sun may be flung into a wide eccentric orbit far from the core, ejected into intergalactic space entirely, or remain comfortably within the main body of Milkomeda. Even if bound to the merged galaxy, the night sky from any surviving planet will be transformed instead of the thin Milky Way band. Future observers would see a dense field of stars stretching across the entire sky, the combined stellar population of 2 major galaxies blended into a single glowing sphere. Meanwhile, the merger will exhaust much of the available gas through the triggered starbursts. Star formation will spike dramatically during the collision phase, consuming gas reservoirs built up over billions of years. After the merger completes and settles into equilibrium, new star formation will slow dramatically as gas supplies dwindle. The youngest, brightest blue stars will live short lives and die, gradually leaving behind only long-lived red and yellow stars. Over tens of billions of years, Milkomeda will fade from blue to yellow to red as its stellar population ages, eventually resembling the giant elliptical galaxies dominating galaxy clusters today. Long before the Andromeda collision, our Sun will undergo its own transformation. In roughly 5 billion years, it will exhaust its core hydrogen fuel and expand into a red giant, likely engulfing Mercury and Venus and possibly consuming Earth. What remains will eventually shrink into a white dwarf, slowly cooling over trillions of years. By the time Milky fully stabilizes, the Sun will be a cold, dark remnant drifting through a galaxy vastly different from the one in which it formed. After Milky forms, it will continue absorbing smaller local group members, including the Triangulum Galaxy and various dwarf galaxies. Over tens of billions of years, the entire local group will coalesce into a single massive structure, an island of light containing perhaps 1.5 trillion stars, completely isolated from the rest of the cosmos. This isolation results from dark energy's accelerating expansion. Currently, galaxies beyond our local group are receding, and this recession accelerates over time. Within roughly 100 billion years, every galaxy cluster beyond the local group will have moved beyond the cosmic horizon, their light stretched to undetectability. Future astronomers within Milky will observe only their own galaxy against an utterly dark sky, with no evidence that other galaxies ever existed. Even within isolated Milky, evolution continues. Over hundreds of billions of years, gravitational interactions will gradually eject stars from the system through close encounters. The galaxy will slowly evaporate, losing stars to intergalactic space while its core contracts and heats. Star formation will have ceased entirely once all gas is consumed, leaving only stellar remnants, white dwarfs, neutron stars, and black holes orbiting in the darkness. By 10 to the 15th power years, the galaxy will have dissolved entirely, its stars scattered across a universe so vast and empty that even light from neighbouring remnants will never arrive, each stellar corpse drifting alone through absolute darkness in an eternally expanding cosmos. The local bubble and interstellar cavities. The Sun doesn't drift through a uniform sea of interstellar gas, but resides within a vast cavity carved into the galactic disk, a region called the local bubble, stretching approximately 1,000 light-years across and filled with exceptionally hot, low-density plasma. This bubble is one of countless similar structures permeating the Milky Way's disk, each representing the aftermath of ancient stellar violence. Understanding these cavities reveals how supernova explosions and stellar winds sculpt the interstellar medium on scales bridging individual stars and the galaxy's overall structure, creating a porous, foam-like texture to the space between spiral arms, where gas density varies by factors of thousands over relatively short distances. The local bubble was discovered gradually through observations revealing that the immediate solar neighbourhood contains far less neutral hydrogen and interstellar dust than expected. Early radio surveys mapping the 1 centimetre emission from hydrogen showed a distinct deficit surrounding our position, while X-ray observations detected faint emission from hot plasma filling this region. The bubble's walls, where it interfaces with denser surrounding gas, show up as shells of neutral hydrogen and dust visible in infrared surveys. These observations revealed that the Sun sits not in typical interstellar space, but within an excavated cavity whose properties differ dramatically from the general galactic environment. The bubble formed through sequential supernova explosions from a group of massive stars that lived and died over the past 10 to 20 million years. When a massive star explodes as a supernova, it releases enormous energy, roughly 10 to the 51st ergs, driving a powerful shockwave into the surrounding interstellar medium. This shock compresses and sweeps up gas, creating an expanding shell of dense material with a hot, low-density cavity behind it. A single supernova can excavate a bubble roughly 30 to 50 light-years across before the expanding shell stalls. But when multiple supernovae explode in the same region over millions of years, their overlapping bubbles merge into vast superbubbles that can span hundreds or even thousands of light-years. The local bubble likely originated from the Scorpius-Centaurus Stellar Association, a group of massive stars located roughly 400 to 500 light-years away. This association contains numerous hot, luminous O and B-type stars, the types that end their lives as supernovae after only a few million years. Computer simulations show that if 15 to 20 supernovae exploded within this region over the past 10 million years, their combined energy could excavate a cavity matching the local bubble's observed size and properties. The most recent supernova contributing to the bubble's formation may have occurred only a few million years ago, recent enough that the bubble hasn't yet had time to collapse or refill with cooler gas. Inside the local bubble, gas density drops to roughly 0.005 atoms per cubic centimetre, about 1/100th the density of typical interstellar space, and far lower than the dense molecular clouds where stars form. This near vacuum contains primarily hot plasma at temperatures around 1 million degrees Kelvin, heated by the supernova shock waves that carved the cavity. At such temperatures, electrons are stripped from atoms and the gas glows faintly in soft X-rays, detectable by space-based observatories like ROSAT and the Diffuse X-ray Spectrometer. This hot plasma is so tenuous that it exerts negligible pressure, allowing the bubble to persist for tens of millions of years before cooler gas gradually flows back in to fill the void. The bubble's boundaries are marked by walls of compressed neutral hydrogen and dust pushed outward by the expanding supernova remnants. These walls show up clearly in maps of interstellar reddening, the dimming and reddening of starlight as it passes through dust. Stars within the local bubble appear brighter and bluer than they would if viewed through normal interstellar material, while stars just beyond the bubble's edge suddenly appear fainter and redder as their light traverses the compressed shells. This transition helps astronomers map the bubble's three-dimensional shape, revealing it's not perfectly spherical but somewhat elongated, possibly due to interactions with other nearby bubbles or the galaxy's magnetic field. The local bubble connects to other similar structures through channels and tunnels in the interstellar medium. To the galactic north, it appears to merge with another cavity called the Loop I bubble, excavated by different supernova events. These connected voids form a network called the local chimney, a pathway through which hot gas can flow from the galactic disk into the halo above. This vertical structure may allow material heated by supernovae to escape the disk entirely, contributing to the galactic fountain, a circulation pattern where hot gas rises into the halo, cools, and eventually falls back as cooler clouds that can participate in future star formation. The Sun's position within the local bubble isn't coincidental but reflects a selection effect. Stars form in dense molecular clouds, but those clouds are typically found in the compressed walls of bubbles rather than in their evacuated interiors. The Sun likely formed in such a dense region roughly 4.6 billion years ago, but stellar motions have since carried it into the bubble's interior. Our current location provides an unusually clear view of nearby stars and interstellar structures precisely because we're looking through very little intervening dust and gas. If the Sun were positioned in a typical dense region of the spiral arms, our optical view of the galaxy would be significantly more obscured. The local bubble also affects cosmic ray propagation and the solar system's interaction with the interstellar environment. Cosmic rays, high-energy particles accelerated by supernova shocks, fill the bubble and influence its thermal structure. The bubble's magnetic field, though weak, guides these particles and affects how they scatter through space. Additionally, the solar system is currently passing through a small cloud of denser material within the bubble, called the local interstellar cloud, which has measurable effects on the heliosphere, the bubble of solar wind surrounding our planetary system. This cloud contains only about 0.3 atoms per cubic centimetre, but is significantly denser than the surrounding bubble plasma. Bubbles like the local bubble exist throughout the galactic disk, creating a complex, multi-phase interstellar medium with gas at vastly different temperatures and densities coexisting in adjacent regions. Large-scale surveys reveal that much of the disk's volume is occupied by hot, low-density plasma in bubble interiors, while most of the mass concentrates in cooler, denser shells and clouds. This structure profoundly affects how stars form, how gas cycles through the galaxy, and how energy from stellar death redistributes through the interstellar medium. The bubbles act as pressure valves, allowing energy to escape vertically into the halo rather than building up destructively within the disk. Understanding the local bubble provides crucial context for interpreting observations of the Milky Way's structure. Many surveys measure gas density, dust extinction, or star counts as proxies for the galaxy's properties, but these measurements are biased by our position within an atypical low-density region. Correcting for this bias requires detailed models of the local bubble's structure and how it affects different types of observations. Similarly, studies of interstellar chemistry, dust properties, and radiation fields must account for the unusual conditions in the bubble to accurately represent typical galactic environments. Future studies will continue refining our understanding of the local bubble's structure and evolution. The Eurosita X-ray telescope is conducting the first all-sky survey with sufficient sensitivity to map the hot plasma throughout the bubble in detail, revealing temperature and density variations that constrain models of how supernova energy propagates through the interstellar medium. Combined with data from Gaia tracking stellar motions and positions, astronomers can identify which stars likely contributed supernovae to excavate the bubble and predict when the next nearby supernova might occur, potentially expanding the cavity further or triggering new star formation in its compressed walls.